Hi, welcome to your lesson on probability tree diagrams. All our work in probability has led us to this moment, and we will see all our knowledge about independent and dependent events come together in this lesson. Let's begin with a flashback. This is always a good time to look back on all the key formulas and things we've learned in probability. So let's take a look. First of all, we began with the idea of complementary events. So we have probability of A plus probability of A naught. So this would be A naught would be everything outside of A, and those two add up to 1 because A and all the things outside of it give you your full range of outcomes. So therefore, probability of A naught is 1 minus probability of A. Just rearranging that formula. That's a key idea. We've come back to that many times. Then probability of A or B. Whenever you see or, we call that a union. And that formula, which we've also used many times, is this. You add up the two probabilities, you subtract away the intersection, and you get your union. And the union, again, represents everything in both circles. After that, we looked at mutually exclusive events. And for those, when we have and or intersection, the intersection does not exist. There is no probability of that occurring because there is no intersection. For or union for those, all we do is add up the A events and B events. And again, since there's no intersection, we don't need to do the subtraction of any intersection. For independent events, we learned that when you have one event followed by another or one event and another, we can just multiply those probabilities to get the probability of both happening. And then for dependent events, we had a similar formula for intersection. We multiply the two probabilities, but the second probability is a probability dependent on the first happening. Those formulas are exactly the same, just a different probability here. And that second formula can be arranged into this when we solve for that. So great summary in 2 slides of all our formulas. Let's move on. So for our warm-up, we'll try this problem. First of all, please read there and fill in the missing blanks in this table. So here are the values that should have been in the blanks. Check your work, double check you have that. And now it says, by completing this table, find the probability a student prefers to watch television, given that the student is a boy. So to do that, we can write it like this: probability of watching television, given that it is a boy. From the table, basically that's saying who prefers to watch TV out of the boy group. So here's TV watchers, 13 TV boy watchers out of the total boys. The other way to look at that is in terms of our formula for conditional probability, which tells us when we have a conditional statement like this, and again, that's this formula right here. When we need to find a conditional probability, we can set this up. So that looks like this. So when we see TV given that boy, we find that TV and boys, so the TV watchers that are boys, and we divide by, again, when we have given that a certain group, we divide by that group, so we divide by the group of boys, because we're saying rather than looking at all students, we're now just looking at the boys. So look at that carefully again, that's an important idea. Okay, next question, try this one. Read this and see if you can solve for this. Okay, this one's kind of tricky in its setup, but let's take a look. So first of all, here's a Venn diagram. We're given the intersection, so the intersection of A and B is here, 0.3. We are also given the probability of A intersection B naught, which happens to be this part here. So this portion of A that is not B, right? So it's, when you read this, it's like A and not B. So if this is all A, this portion here is A things that are not B. So that's where the other 0.3 goes. And now that you have those two, you know the entire A is 0.6. So we can use our independent events formula because it tells us these are independent. Which tells us the intersection is probability of A times probability of B. And we just got A to be 0.6. We know the intersection is 0.3 given to us, and then this is the unknown. We can solve for it here. Now that we know that, we can find the union by using the union formula. And there's all the values. Here's A, here's B, which we just found here. Here's the intersection. That allows us to solve for the union, which is 0.8. So bringing together 2 of our key formulas, and that's often how these exam problems work for the probability. There's like our 3 or 4 key formulas, and you have to just read the keywords, figure out which formulas to use and how to use them. All right, so now we're moving on to looking at probability and how it's represented visually. So we've looked at ways of, for example, if we toss 2 coins, Here's heads, tails on one coin, here's heads, tails on another. We've looked at creating diagrams like this, like sample space diagrams or two-way tables. They help us kind of visualize all the outcomes. So here we have 4 different outcomes for this scenario. But another way to show different outcomes in probability is to use what's called a tree diagram. And I know you've seen these before, but this is the first time we're bringing them up in this course. So here's a tree diagram for the same situation. Here's our first coin. We can get heads or tails. Here's the second coin toss, heads or tails on that one as well. And here, if you follow the paths, you will notice there's 4 paths. There's this path, heads, heads, or this one, heads, tails, or this one, tails, heads, or the last one, tails, tails. So those 4 paths represent the same thing we can see in this sample space diagram. So basically all our outcomes are represented here as well. So it's a good way to visualize the sample space. So in this lesson we'll concentrate on these tree diagrams. So here's another example of that. Again, we looked at, let's say you roll 2 dice. Here's a sample space diagram, right? Here's die 1, die 2, here's all the possibilities, and we know there's 36 possibilities. So sample space diagram gets filled up pretty quick, but oh, here's another way to show that, right? Here's with all the things, here's with the total scores. So 6 and 6 makes 12, for example. But also we can represent that with a tree diagram too. So if you're looking at that, you're like, there's so many outcomes there. Well, the tree diagram shows all those outcomes as well, because here's for the first die roll, 1, and then after you roll 1, you can roll 1 to 6 on the second die as well, and you get all those choices. And if you can see here, there's 36 choices. But here as well, there's 36 final branches. So there's 36 choices represented there as well. So both of them lead to a big sample space. And in different scenarios, one or the other will be a better choice to use. For 3 or more events, though, because this is just, that last one was 2 events, right? 1 die roll, another die roll. But let's say you have 3 or more. A sample space diagram is impossible, because a sample space diagram is a 2-dimensional thing, right? There's 1 axis here, 1 here. But once you have 3 events, for example this, you're choosing a side dish, a main dish, and a dessert. There's no way to represent that in the sample space diagram, because you can't do that. This is a 3-dimensional set of information here. So here you must use a tree diagram. So that's an advantage of tree diagrams. They're more useful when you have more and more events occurring. So here's an example of that. Let's say you toss a coin, heads, tails, and then you toss a second coin, heads, tails again, and then you do a third toss, heads, tails again. We need a tree diagram for that, and we can follow all the paths. And we can see in the end if you count these, there are 8 final paths. So that's 8 final outcomes. For example, the heads, heads, heads path, or heads, tails, heads path, and so on. So how many possible outcomes are there? Well, that's all of those there, and there's 8. Now, question 5, what's the probability of getting 1 head only? Let's take a look. 1 head only will be all the paths that lead to 1 head only. So for example, that path leads to 1 head only, or this path leads to 1 head only, and then there's a third one here that leads to 1 head only. So you can see at the end of each path, let's see, this one was head, tail, tail, so 1 head only. The second one was tail, head, tail, 1 head only again, and this last one also tail, tail, head, so 1 head only. So we see 3 paths that lead to 1 head only, and that means our probability of getting 1 head only is 3 paths out of 8. However, that's looking at counting paths, and that only works in terms of counting paths here if we had all these same probabilities here, which we do. The probability of head or tail is always a half everywhere, so we can just count the paths. But the proper way to do this, if these probabilities were not all equal, it wouldn't work that way. So you have to actually follow each path and see what happens. And when you follow one path, all you do is multiply the values along the path. So the probability of getting a head, tail, tail like we have here is 0.5 times 0.5 times 0.5, because those are independent events, right? So we can just multiply those. Multiply those and you get 0.5 times 0.5 times 0.5 is 1/8. So one of those paths has a probability of 1/8 of occurring. And then another path there as well has a 1/8, and then this third path here has also 1/8, and if you add those paths up, you get 3/8. So it matches the idea of saying 3 out of 8 paths, but also find the probability along each path, and they also add up to 3/8. And that works coincidentally here because these are all 1/2 probability. Okay, so let's look at a problem now where we have our tree diagram. We're going to set it up. So read this problem and see if you can fill in the blanks on the probability tree diagram. And let's say, what are the probabilities of getting a hit here and a miss here? So check your tree diagram now. Here are all the values. And to answer the question I just asked, we have 0.8 and 0.2. However, make sure you see all the other ones. The main thing to consider here is that it says when this student takes these shots, we're assuming that his success is on one shot is independent based on his previous shot, right? So he takes one shot, his next shot, he has the same probability of getting the bullseye or not. He just is such a good shooter. He's very consistent. It's always the same probability. And we can see that consistency here. He hits, and then his probability of getting hit the next time is the same. His probability of getting missed the next time is the same. This is independent. So to find these probabilities, let's give it a try using the tree diagram. So for number 1, to get a hit and then a hit, that means 2 bullseyes, it's 0.8 times 0.8. Again, they're independent, so you just multiply them. Next one, we have a hit. Hits only 1 bullseye. Well, that means hit and a miss, or miss and a hit. Remember that we did that before, where we have one situation, or union is or another situation. So that would be hit miss right here, or plus miss hit, and you have to add those up to get the chance of getting at least only 1 bullseye, and that's 0.32. So if you did only one of those paths, remember you have to think about both those paths because they lead to that 1 bullseye situation. And then the third question, hits at least 1 bullseye. Well, that's like saying everything but him missing both. So we use that complementary events situation here. 1 minus the 2 misses, and the 2 misses are 0.2, 0.2. So at least 1 hit is everything but those, which is 0.96. If you did it without using complementary events, hopefully you noticed it's 3 paths. It's the hit path, hit miss path, or miss hit path. It's those 3 paths which will give you the same answer as this. Okay, next question. Same student taking shots, but now we're going to look at a dependent situation. That means if he hits the bullseye on the first shot, then his next shot is 0.85 probability of hitting the bullseye. So that means he makes 1 hit, and now he's gotten some extra confidence and he's more likely to hit a bullseye the next time. Or contrary to that, if he misses the bullseye on the first shot, then his next shot has only a 0.75 probability of hitting bullseye. So if he misses one, his confidence goes down a little bit. So now this is a dependent situation. Let's see if you can fill the tree diagram. What are all the values? Let's say that go here and here again. What are those values? Okay, check your work. So here's all the probabilities there. Now these change because of dependence, and I asked about these two, so I hope you see why those work out the way they do. And then these ones as well, take a look, they're different. Okay, so now can you answer this question? Let's take a look at the work. So we're looking at he hits the bullseye exactly 1 time. So that means either he hit missed or he missed and then hit. So both of those have to be, both those paths have to be considered. So the 0.8 times 0.15 path and then the 0.2 times 0.75 path. Add those up and you get your total probability of 0.27. This is a pretty standard question for tree diagrams. Just make sure you study that carefully if that didn't go well for you. Okay, next one, try this one. Try both questions there. And let's check our work. So here's the answers for this. Notice here we have the dependence, so this goes down. And we're looking for at least 1 green. Again, we can do 1 minus both red to get at least 1 green. Or you can add up all 3 paths that have either 1 green or both greens. And question B is an important one. We're looking at least 1 green, pick a green given that at least 1 green is chosen. So that's a dependent situation. And remember, when we have given that, we do the bottom of the fraction is the probability of that, whatever the given situation is. So given that 1 green is what we found out in A, that goes on the bottom of this fraction, that 8/11. And on top we have picks a green on the first pick, which is only this path here, 5/11 times 6/10, and that is divided by the at least 1 green. Oh, sorry, red on the first is here, so 6/11 times 5/10. So that's red and green, and then at least 1 green. Again, this is kind of tricky, so make sure you study this carefully. Okay, one more, try this one. And these are the questions here. And now check your work. This one's a little tougher. Check your work carefully. Pause the video if you need to. And we'll continue in the next video about tree diagrams for a familiar problem that we may have seen recently. So there'll be one more video for you to study. It'll look at a familiar situation. Again, make sure to study this one because this one's pretty tough.